Welcome back, everybody. Today we're going to finish up section 1.5. We are looking at solving inequalities again, but this time they're what we call compound inequalities. And there are two types of compound inequalities. There's the and type and there's the or type. And it is important that you make that distinction between and or. An and inequality, we need to find the solutions that make both inequalities true. So we are looking for where they overlap. So in our first example, what is the solution of 7 is less than 2x plus 1 and 3x is less than or equal to 18? We need to graph and find the solution for x that fits both of those statements. So we're going to solve them separately for this first one. To solve or to get x by itself, we're going to subtract a 1 first. Then we have to deal with the 2 that's getting multiplied, so we're going to divide that out. And we have the statement x is greater than 3, or 3 is less than x. Again, remember you start typically from the variable, and in this case we have to read backwards. X is greater than 3. So we need an open circle at 3, and we are shading everything greater than that. For the second one, all we have to do to solve this one is divide out the 3. And we have the statement x is less than or equal to 6. So we'd have a solid dot at 6, and we're shading all the numbers less than that. So what we are looking for is that overlapping section. Where have we shaded for both lines? And in this case, we are looking at the space here from 3 to 6, where we have shading for both. Now notice that on this first one, we have an open circle. So we are going to have to keep that because 3 is not being used on our blue graph, and it is on our red. It has to be used on both to count. So we are going to have an open circle on 3. And then if you look at the 6, you'll notice that we are shading it here, and it's a solid dot here. So it is included on both of those. So solid dot at 6, and we want everything in between. So our solution is we want all the x's that are greater than the 3 and still less than or equal to the 6. So let's try another one. Again, we're going to split it up. Once you get the hang of this, you don't necessarily have to have 3 separate number lines. You can probably figure it out on one. So what is the solution of 5 is less than or equal to 3x minus 1 and 2x is less than 12? So on the left inequality, I'm going to add 1. So I have 6 is less than or equal to 3x, and then I have to divide out my 3. So I'm going to end up with 2 is less than or equal to x. Right? Again, reading from the x, x is greater than or equal to 2. So solid dot and shading to the right. For this one, we have 2x is less than 12. We're going to divide out the 2, so we have x being less than 6. So from 6, we'd have an open circle because it's not equal to it, and we want all the numbers that are less than. So again, looking for that overlapping section, it would be things in between here and here. So we would graph, since both the blue graph has a solid dot at 2 and it is completely shaded on the green graph here, we are going to have a solid dot at 2. But because of this open circle on 6, we can't include that. So open circle, and we want all the numbers in between. So our final solution, we want our x's to be in between 2 and 6. It can equal the 2 and be bigger, but it has to be smaller than the 6. If the variable part of an and inequality matches, then we can collapse it. So for example, if I said 5 is less than or equal to x plus 1 and x plus 1 is less than 13, because these are the same, we can collapse this down into one, what we'd call a compound inequality. Keep in mind that this really stands for 2 separate inequalities. We've just been able to combine them. So we really are solving 2 inequalities at the same time. So looking at this, to get x by itself, I'm going to have to subtract a 1. But remember, it came from two separate inequalities. So I'm actually going to have to subtract that 1 from both sides. So 5 minus 1 would be 4, 13 minus 1 would be 12. We want all of the x's that are in between 4 and 12. So since there's no equal signs on those, I'm going to have open circle. 12 would be about there. And we want all the values in between those. All right. Let's check out a couple that might be a little bit tricky. We're going to have to think about these a little carefully. To solve this one, negative 2x is greater than negative 12, we are going to have to divide by a negative. If you remember from the other day, that means we have to reverse our inequality. So now we would have x having to be less than a positive 6. And at the same time, to solve the second one, we'd have to add a 2. So we're going to have x having to be greater than 13. So we want x to be smaller than 6 and at the same time bigger than 13. Well, if we tried to graph that, here's 6, 13 is going to be over here. We want to be smaller than 6 and at the same time bigger than 13. There is no overlapping section there. So we would on this one say no solution. All right, our next example, we have x divided by 3 is greater than 1. To solve this, I'm going to multiply both sides by 3. So I have x is greater than 3. And to solve the second one, x plus 1 is greater than or equal to 8. I'm going to subtract a 1, and I'd have x has to be greater than or equal to 7. So picture on this one, we want to be greater than 3. And we want to be greater than or equal to 7. All right. So if you think about where they overlap, our overlapping section would be everything from here, this direction. All right. So we do have a solid color, both on the first inequality and the second one because of that solid dot. So my final answer would be everything from 7 on up. Okay, so we'd say x is greater than or equal to 7 would be the overlapping part. All right, the second type of compound inequalities are the ones we call OR. In this case, we're looking for all the values that make either of the inequalities true. Okay, they don't both have to be true. We just have to make sure that either one can be true. What is the solution to 5 minus 2m is greater than or equal to 21, or 4m minus 1 is greater than or equal to negative 21? So let's start solving the one on the left. I'm going to subtract 5 to undo that positive 5 that's there. 21 minus 5 would be 16. I am going to have to divide by a negative 2. So I'm going to have to reverse my inequality. So m is going to have to be less than or equal to negative 8. Or, for the second one, we're going to add a 1. Negative 21 plus 1 would be negative 20. I am going to divide, but just by a positive 4, so nothing has to change for my inequality symbols. So I have m has to be greater than or equal to negative 5. Now this is an OR situation, so we want to shade both of these because it can, either one of them can work. So for the blue one, we are saying that m has to be less than or equal to negative 8. So at negative 8, I'm going to have a solid dot and shade all the ones that are to the left of that, smaller than that. Or I want m to be greater than or equal to negative 5. So solid dot at negative 5 and shading all of that. We are not looking for an overlap, so we're just going to include both of those pieces because it doesn't matter to us which one fits at any given time. It can be either one. All right, for this one, we have 7w plus 3 is greater than 11, or 5w minus 1 is less than w minus 13. So let's start with this one. To solve this, I'm going to subtract a 3. We have 7w is greater than 11 minus 3 would be 8. So w has to be greater than 8/7 if I divide out that 7. For the next one, 5w minus 1 is less than w minus 13. I need to get my w's on the same side. So I'm going to subtract that 1. And then I'm going to add the 1 to get my constants on the same side. Oops. 4w is less than negative 12. And then I'm going to divide out my 4. So I have w is less than negative 3. Now, this is an OR situation. So my answer is w is greater than or equal, w is greater than 8/7, which would be just a little bit over 1, or w is less than negative 3. Okay, so 8/7, like I said, is a little bit bigger than a 1, and we want to be bigger than that number. W being less than negative 3, we'd have an open circle at negative 3 and shading to the left. And we would include both of those pieces because we're not looking for the overlap here. It can be either one. Again, we're going to watch out for some unique situations that can arise. So let's look at these last two examples here. To get rid of the adding 2, I'm going to undo it by subtracting 2. So y has to be greater than 3. Or to solve the second one, I have to divide by a negative 2, which means my inequality is going to flip. So instead of less than or equal to, it will be greater than or equal to. Negative 18 divided by negative 2 is 9. So if we picture this one, y has to be greater than 3. So here's 3. We want to be greater than 3, or we can equal 9 or be greater than that. Now, we want to include both pieces, but they do overlap a little bit. This one is already included. If we were to extend this, because we can be anything bigger than 3, this part is already included in that one. So your final graph would just need to have the one branch that encompasses both parts. All right, our last one here, we're going to add a 1. So 2z is less than negative 4. Divide out the 2, and we have z has to be less than negative 2. Or, to solve this one, I'm going to get the z's on one side, so I'm going to subtract those two z's to the other side. That leaves me 1z being greater than negative 7. All right, so if we picture graphing this, at negative 2 we want to be smaller than it, or at negative 7 we want to be greater than it. And if we want both of those pieces to be included, we really are shading the whole number line. Because we can go everything from negative 3 this way, we can go everything from negative 7 this way, the net result is that the whole thing gets shaded. So we would say all reals. We do have a symbol for that. It's a capital R with kind of a double bar to it. All right, so we are going to stop there and check your Schoology page for your 1.5B assignment.